So my talk on Dirac actions is, well, it's the development of a theory. My interest in Dirac geometry really goes back to our own theory of Lie group valued moment maps that we developed with Anton something like 16, 17 years ago. And was a very successful theory, I think, but it had one big problem, which was that there were just too many miracles. So everything just worked, and it's not supposed to be like that in mathematics, that everything just works. And so this caused a bit of a problem, which was resolved by work of Marius and Enrique, who explained that everything fits very naturally into the framework of Dirac geometry. And so all these miracles go away. They have natural explanations. Well, this then, of course, sparked my interest in Dirac geometry. So one direction, for instance, that I was interested in is how to unify our theory of group-valued moment maps with the theory of group-valued moment maps due to Jiang-Hua Lu in Poisson geometry. And it turns out that this works very nicely in terms of Dirac geometry. But then once you've gotten this far, it just begs itself that you just develop the theory a little bit for its own sake. And so we don't really have very concrete applications in mind right now. But it turns out it's a nice and rich theory which should have applications that we just need to find. OK, to get started, I want to remind you about definition of Poisson Lie group actions. So as you know, a Poisson Lie group is simply a Lie group with a Poisson structure such that the group multiplication is a Poisson map. So this notion of Poisson Lie group was introduced by Drinfeld as semi-classical limits of quantum groups. And shortly after, Semenov Tian-Shansky introduced the notion of a Poisson action of a Poisson Lie group. So he had encountered examples of such actions in the context of soliton theory. So he had encountered examples of Lie group actions, of symmetries in soliton theory that did not preserve the Poisson structure. And then he discovered that if you put a Poisson structure on the Lie group itself, you get a Poisson map. So this was how Poisson Lie group actions came about. And it turned out this has a very interesting theory. For example, there's this nice classification theory due to Drinfeld. The classification involves the notion of a Manin triple. To remind you, Manin triple is just a triple of Lie algebras. Lie algebra D containing Lie algebras G and H as transverse Lie subalgebras. And the Lie algebra D carries a non-degenerate symmetric bilinear form, which is ad invariant, and such that G and H are Lagrangian. So today, Lagrangian is used for symmetric bilinear forms, whereas yesterday, Lagrangian was usually used for skew-symmetric bilinear forms. So Lagrangian just means it's equal to its orthogonal. Okay, so using the metric, we can and often will identify a Lie algebra with its dual. Okay, then the classification works as follows. So first of all, the Poisson Lie group structures on a Lie group H are classified by, well, H equivariant Manin triples. So this H equivariant you can ignore if the group is connected and simply connected. H equivariant basically just means that H acts on D, preserving H, preserving the Lie algebra H, and compatible with the given adjoint actions of H. So this is the classification of Poisson Lie groups and the classification of Poisson homogeneous spaces. So if you have a Poisson manifold M with a Poisson action of this given Poisson Lie group, the Poisson structures on M for which this becomes a Poisson action are classified by Lagrangian Lie subalgebras of this Drinfeld Lie algebra D. K-invariant Lagrangian subalgebras, with the additional property that the intersection with H is the Lie algebra of K. So these are easily classified, and then you can do lots of examples of that. There's another nice result. I mean, there are many nice results about Poisson actions, and I cannot review them all, but one result that I want to mention is the following. So I just mentioned a moment ago, Poisson actions do not necessarily preserve the Poisson structure on the manifold M. So put differently, well, for any Poisson manifold, you can look at the cotangent Lie algebroid. So the cotangent bundle has a natural Lie algebroid structure. And the action you have on T star M, it does not preserve this Lie algebroid structure. So this doesn't seem so good, but Jiang-Hua Lu many years ago had a nice way of fixing this problem. So what she showed was that if you take the cotangent Lie algebroid and put it together with the action Lie algebroid, so you take the direct sum of the two, then that direct sum has a Lie algebroid structure such that both summands are Lie subalgebroids. And the direct sum has an H action by Lie algebroid automorphisms. I'm preserving the first summand. So this not so good action which you have on T star M is really the quotient action. And she had some nice applications of this result. And it's some of these applications that we want to generalize to the Dirac world. So let me review some Dirac geometry. So as the name says, Dirac geometry was introduced by Courant and Weinstein. And well, one of the motivations was, I believe, to just give a common geometric framework for Poisson geometry on one hand and geometry of closed two forms on the other hand. The name comes from, well, one of its concrete applications, which is, it has something to do with Dirac theory of constraints, mechanical systems with constraints. And the definition, well, with some revisionism is as follows. So we consider the tangent bundle together with this dual, so this double tangent bundle, Tm plus T star M. The direct sum has a canonical bilinear form, which is just given by the pairing of vectors and covectors. And it has this strange bracket on sections. So the bracket of two vector fields is simply the Lie bracket of the vector fields. The bracket of a vector field with a one form is somewhat tricky. So if you look carefully, this strange bracket that we have is actually not skew symmetric. But turns out, I mean, that's in a way the big discovery that these strange brackets are actually interesting and meaningful. So it's a non-skew symmetric bracket. Well, in Courant's original work, as you know, he worked with a skew symmetric version of this bracket. And this bracket, which I'm going to call the Courant bracket, was introduced later by Dorfman. Okay, so given this structure, one defines a Dirac structure on M to be a Lagrangian subbundle of this double tangent bundle. So Lagrangian, again, meaning that it's equal to its orthogonal, with the property that it's involutive. So its space of sections is closed under the Courant bracket. So that's the integrability condition. That's a Dirac structure. And then there are the two main examples, of course. If you have a if you have any two form on your manifold, you can look at the graph of this two form as a subbundle of tangent bundle plus cotangent bundle. And the result is that two form is closed if and only if this graph is a Dirac structure. And likewise for a bivector field, you can look at the graph of the bivector field. So by which I mean the graph of the map from the cotangent bundle to the tangent bundle defined by the bivector field. So that graph is a Dirac structure if and only if the Schouten bracket of the bivector with itself is 0. So if and only if pi is a Poisson structure. So it's both settings, they're nicely unified to one theory. Because then you can look at some Dirac structures which are not graphs of a map from Tm to T star M or from T star M to Tm. So it's these two extreme cases that lead to closed two forms and to Poisson structures. Okay, let me state the key properties of this strange bracket that one has on Tm plus T star m, which is not skew symmetric. So the first property is this kind of Jacobi identity, which says that bracketing with a given element is a derivation of the bracket. And so its Jacobi identity holds in this particular form. Second property is that bracket with some element x1 is also a derivation of the metric in this form. Well, I haven't said what is the anchor. The anchor is, in this context, this map A is simply the map from the double tangent bundle to Tm, simply the projection. So A of x1, if you have a section, A of x1 is just the vector field component of x1. And the third axiom is how does it fail to be skew symmetric? That's this property. So here A star is the dual map to T star m where I identify double Tm with double Tm star using the metric. So it's easy to check what it boils down to being is simply the inclusion of T star m. So x1 paired with x2 is a function. D of that is a one form. And that one form I can view as a section of this double tangent bundle. So you have these three axioms. Okay, I've mentioned these axioms because once you've put it this way, you know how to generalize. And this was done by Liu, Weinstein, and Ping Xu. So they introduced this notion a bit more generally of a courant algebroid. So instead of just looking at Tm plus T star m, we look more generally at vector bundles over M with a metric and some bracket on the space of sections and an anchor map from the bundle into the tangent bundle, which satisfy these same three properties. So this kind of Jacobi identity, the fact that bracket is a derivation of the metric, and then this particular way in which skew symmetry fails. And then in this context, one can again define Dirac structures to be Lagrangian subbundles that are involutive, so the space of sections is closed under the bracket. So one important consequence of these definitions is if you look at this Lagrangian subbundle E and restrict all these three properties to the Lagrangian subbundle E, you see, well, the first property is simply the Jacobi identity for the sections of E. The second property just says 0 is equal to 0. And the third property says that, well, on E, x1 paired with x2 is just 0 because it's Lagrangian. So on E, it becomes skew symmetric. So E becomes a Lie algebroid. So E becomes Lie algebroid, and that's very nice because then you know any Lie algebroid defines a generalized foliation of your manifold, and so that's very nice geometry. So from now on, I take a Dirac manifold to be a manifold M equipped with such a Dirac structure. So there's this courant algebroid and a Dirac structure in it. And just to say it again, this then implies in particular that E is a Lie algebroid and you have this singular foliation of M. Singular foliation, I shouldn't say generalized foliation. So there are leaves of different dimensions. That's all. Okay, so the first example is, of course, a Poisson manifold. So any Poisson structure can be regarded as a Dirac structure. That was already Courant Weinstein's main example. So where your Dirac structure is just a graph of the bivector field. And another example that is important to us, well, you have the same example with two forms, but that's not going to be so relevant for this conference. Yeah, the foliation in the case of Poisson manifolds is just the foliation by symplectic leaves. And I should say the Lie algebroid structure on the graph of pi m is just the same as this cotangent Lie algebroid structure. Right. Another example that's important for us is due to David, myself, where you start out with a Manin pair. So a Lie algebra with a non-degenerate metric, invariant metric, and a Lagrangian Lie subalgebra. And you suppose you have a Lie algebra action of this bigger Lie algebra with a property that all its stabilizers are coisotropic in D. So coisotropic meaning the orthogonal space is contained in the stabilizer. So if that's the case, then you can just take the trivial bundle M times D as a Courant algebroid. So what I'm saying is the trivial bundle M times D has a Courant bracket extending just the Lie bracket on constant sections, and with the anchor map being the action map. And M times G then becomes a Dirac structure. So there are many examples of Dirac structures which arise in this way. So from actions of Lie algebras with coisotropic stabilizers. I remember that when David started working with me as a student, this was the first problem I asked him to look at, and he figured it out within like 2 days.
So then your foliation is by
Yeah, so in this case, the foliation you have is just the G orbits. Of course, there's another foliation which is given by the D orbits, and that's the case in general. Okay, we will also have to talk about morphisms of Dirac structures. And just like yesterday, morphisms are defined by Lagrangian relations. So this notion of Courant morphism was introduced by Enrique Iglesias Ponte and Pavel Cervera. And the definition is, well, you have two Courant algebroids over manifolds M1 and M2. Then a Courant morphism is a map of the underlying manifolds, phi, and then a Dirac structure along the graph of that manifold. I haven't really defined what a Dirac structure along a submanifold is, but let's just skip that part. So that's Courant morphism. It's a Lagrangian relation, if you want. And if you have Dirac structures, then we say such a Courant morphism defines a Dirac morphism if every element in E2 is related to a unique element in E1. And so this Courant morphism, it's not a map, it's a relation, right? Because it's a graph. And so you can say elements of A2 and A1 are related. And the definition of Dirac morphism is that I'm going to use is that every element in E2 is related to a unique element in E1. So it comes from a unique element of E1. So this uniqueness part is very important to me. So there's another definition of Dirac morphism where you just skip the uniqueness. But I'm going to insist on this uniqueness part. It's some sort of transversality condition. And I'm going to get back to this in a moment. So for example, if you take these standard Courant algebroids, where you just take tangent bundle plus cotangent bundle, then any map of the underlying manifolds defines such a Courant morphism. You just take the graph of the tangent map together with the graph of the cotangent map. That's the Courant morphism. And then one can check, again, with this uniqueness condition, that for Poisson manifolds, what does it mean for this standard lift to be a Dirac morphism? It means exactly that it's a Poisson map. And so if your Dirac manifolds are Poisson manifolds, then the Dirac morphism between them are just the Poisson morphisms. There's nothing new. Okay, now composition of Courant morphisms, of course, is defined as compositions of relations. But just like we had yesterday, there's some problems there because you need to impose some transversality conditions for, so it doesn't really have to be transverse. It could be something like clean intersection or whatever. But you need to impose some conditions for the composition to be a subbundle again. So that's a little bit bothersome. But the good news is, if you don't look at Courant morphisms, but if you actually have Dirac manifolds and you look at Dirac morphisms, then these transversality conditions are automatic. So that's very good. So that's why I need this uniqueness assumption. This one transversality condition that ensures that composition of Dirac morphisms is always transverse. And so you can always compose them. And so it means that we actually have a category of Dirac manifolds and Dirac morphisms. So the objects are the Dirac manifolds, manifolds with a coherent algebroid and Dirac structure in it, and the morphisms are the Dirac morphisms. Yeah, so what I've used here is the forward Dirac morphisms. And so the uniqueness assumption is sometimes called strongly forward Dirac. You could cook up another category where you work with backward Dirac morphisms. So our definition of Dirac morphism is such that at any point in the image, this fiber is obtained as a composition. So this would be the fiber at phi of mm, composed with E1 at m. So it's a composition of Lagrangian relations. And then, so this is forward Dirac, but you could also do a Dirac, a backward Dirac definition, which goes something like this. But this we're not going to consider here. But these backward Dirac maps, they also appear in practice. Okay, so we have the Dirac category, we have the Poisson category, of course. And sometimes I like to look at this category of Lie algebroids, where the morphisms, however, are what's usually called co-morphisms of Lie algebroids. That's just the way it naturally arises in our context. For example, if you look at cotangent Lie algebroids of Poisson manifolds, you have a map from M1 to M2, then you have a map from TM1 to TM2, but then for the cotangent bundles, the map goes the other way, so that's why it's a co-morphism. But it's compatible with the Lie bracket, and it's a Lie algebroid co-morphisms. So these three categories play a role. And there are natural functors between them, right? Because every Poisson manifold can be viewed as a Dirac manifold. And for any Dirac manifold, you get a Lie algebroid by just forgetting about the coherent algebroid. Right? I mentioned E is always a Lie algebroid. All right. So at this stage, I could already go and talk about Dirac Lie groups, but before doing that, I want to apply this Dirac theory to Poisson geometry. This is not completely new, but I think it's very nice to see how in the framework of Dirac geometry, some classical constructions in Poisson geometry look just very natural. So suppose you have a Poisson action of a Poisson Lie group on a Poisson manifold. Then you can cook up an action of H on this double tangent bundle by simply taking the direct sum of the action on Tm and the action on the graph of pi m, so the cotangent Lie algebroid. This is a somewhat tricky thing to do, so let me draw the picture. So this is Tm. This is T star m. So if you have an action of H on m, there's a natural lift to Tm plus T star m. But that's not the action we use. The action we use is, well, there's the graph of the Poisson bivector, which is, of course, identified with T star m. And the action we use preserves this decomposition. It doesn't preserve that decomposition. So it's a different action. But it's a very simple definition of an action. And at first sight, it looks like this is actually a somewhat stupid thing to do, right? Because this action doesn't seem to be very good. It does not preserve the courant bracket. This natural lift preserves the courant bracket, but here's no reason why it should preserve the courant bracket. And in fact, it doesn't, because, as I mentioned before, the action on the graph is not by Lie algebroid morphisms. But it turns out that this is actually a useful thing to look at. Because even though it does not preserve the courant bracket, one finds that the space of invariant sections is closed under the courant bracket. It's a similar thing in Poisson geometry. So the H action does not preserve the Poisson structure, but the space of invariant functions is a Poisson subalgebra nonetheless. Okay, so this means that if, for example, the action of H on M is free, then I can simply take a quotient by H, and I get a new Dirac structure. And this is something we can apply to the example where my Poisson manifold is just the Poisson Lie group itself, with the action given by left multiplication. Right? So it means that if I take the current algebraic which I have over H, which is just double TH, and quotient by this strange bullet action of H, it's a Lie algebra, because it's a current algebra over a point. It's a matrized Lie algebra, because the current algebra over a point. And apply the same thing to the graph of the bivector. That's going to be a Lagrangian Lie subalgebra. And then, of course, I can apply it also to TH, which is also a Dirac structure, and I get a complement. So I immediately get the Manin triple, just quotient by the action of H. Oh, beta is, yes, so sorry, beta is my notation for the metric which you have on D. Yeah, I always like to tag it on as some index, because later we sometimes take beta to be degenerate. So it has some meaning. Okay, so you immediately get this Manin triple. And it's an H-equivalent Manin triple because on double TH, I mean, this strange bullet action that I'm working with, it came from the left action, from the action by left multiplication. But there's another action of H by right multiplication. And those two actions commute. And so for right multiplication, I just take the standard lift. And that then descends to the quotients, and so it acts on these things. So that's why I get an H-equivalent Manin triple, quite simply. All right, and of course you can then also use this then to define a trivialization. So this is the trivialization which you get of all our structures using this bullet action. And using the fact that everything is H-equivariant for the right multiplication, you can easily figure out what is the anchor in this case, and you get this formula, which is the formula for the dressing action. Right, so all these data you can quite easily just calculate. And conversely, given your H-equivariant Dirac Manin triple, you can go back, right? You can just write down this current algebroid as an action current algebroid, because you know what the action is supposed to be. You have your Dirac structure, and so you just write this down, and then you have to identify H times D with TH plus T star H. But that's also easy, because TH is already sitting inside H times D, and so it's a very short proof of this Drinfeld classification in this case. So it's a short proof, and remarkably, you never have to do any Poisson bracket. Everything is just linear algebra, basically. Yeah, so this was the classification of Poisson Lie groups. So for Poisson homogeneous spaces, it works similarly. And so here it really shows the power of Dirac geometry. So if you have a Poisson homogeneous space, then what one can do in Dirac geometry, I don't really have time to explain it too much, is you can pull back the Dirac structure. So pullback of a Poisson structure under submersion is not defined, but pullback of Dirac structures is defined. And so you can pull back the Dirac structure, the Poisson structure as a Dirac structure. And so you get a Dirac structure in this double TH. Then you check, because the Poisson structure was invariant under this bullet action, this new Dirac structure is also invariant under the bullet action on double TH. And by the way, I should maybe say how's the pullback defined. So the way the pullback is defined is simply, so as a Lie algebroid, this L is simply, okay, so we have this map H to M, which is H mod K, projection map, and we have some Dirac structure over M, let's call it Q. Then you define the pullback, so we have some Lie algebroid over M, which is Q. So in our case, it's the Dirac structure. And then the pullback is defined simply as a fiber product over Tm. So we here use the anchor map, and here you just use the projection. And by the way this pullback operation goes, L then also has a K action from the right multiplication, because again, this bullet action came from the left multiplication. Okay, so as on the previous slide, we can simply take the quotient by the bullet action, we get a Lie algebra. A Lie subalgebra of D. And it's K invariant. And the fact that L intersect TH is the kernel of the differential, this implies that L intersect the Lie algebra H is K, as desired. So a very short proof of this Drinfeld classification. If you look at Drinfeld's original paper, this is pretty much how he did it, except that he didn't have the language of Dirac geometry. Yeah, but one can so the classification, of course, you also have to be able to go back, and that's rather straightforward too. So given L, you just write H times L, and you take a sort of symplectic quotient. I should mention this construction, as I said, is not new, and it was done in a more general setting of Poisson groupoids by Liu, Weinstein, and Xu as one of the applications of current algebroids. All right, but now I should go to Dirac Lie groups. Any questions about this? So let's then go to Dirac Lie groups. So here's my definition of a Dirac Lie group. So we define a Poisson Lie group to be a Poisson manifold with a multiplication such that group multiplication is a Poisson map. And I try to define Dirac Lie group in a similar way. So it's a Dirac manifold, and there should be a multiplication morphism. But it turns out I also need something which plays the role of a unit morphism. So it has a multiplication morphism from H times H into H, and it has a unit morphism from the point with the trivial Dirac structure into H. And it satisfies properties of associativity, and then the obvious properties that you would write down that this unit morphism is a unit. So those are the axioms that I impose. I'm not saying anything about inversion. Well, in Dirac action, we define similarly. So it's given by some action morphism from H times M into M. So everything is Dirac manifolds. And it should satisfy the action property for these morphisms. Right, so even though these morphisms are just morphisms, they're not map, I can compose them, and I can just write down the usual axioms. And so there's action property, and then there's a property which I didn't write down, that the unit acts trivially. So we don't mention inversions for some good reason. So in Poisson geometry, you also don't like to talk about inversions because inversion for Poisson Lie group is anti-Poisson. So we're trying here to make the definition of Dirac Lie groups somewhat categorical, but there are well-known problems with the categorical definition of Poisson Lie groups. Sorry, there are already well-known problems in categorical definition of Poisson Lie groups, because for one thing, inversion is not a Poisson map, and the other problem is, as was pointed out by Alan in one of his recent Poisson talks, that direct product of Poisson manifolds is not a direct product in the categorical sense. This then comes automatically because it's the base, right? It's just like I mean, if you're working with manifolds and you you have a multiplication which is associative and you have a unit, then it's automatic that you have a smooth inverse. No, but just because the base of A is automatically a group. Okay, so those are the definitions. And again, automatically a lot of nice structure comes along with that. So our original definition of Dirac Lie group was actually a bit more complicated. We first assumed that the total space of this Courant algebroid has a groupoid structure. And it turns out that that's automatic. So using the axioms from the previous slide, one can show that the Courant algebroid has a groupoid structure, with this Dirac structure being a subgroupoid. I'm going to show in a moment an example of how this works. Oh, VB means a vector bundle. So it's not only a groupoid, but everything is vector bundles, and all the structure maps are vector bundle morphisms. So the source map is a vector bundle map, and so on. So G is something that pops out from the theory. So at this point, it's just a vector space. But it turns out eventually that it's automatically Lie algebra.
Which piece of data does it come from? The multiplication already from the Dirac structure?
It uses the Dirac structure. So yeah, you go back. So the proof takes me like 1.5 pages, but it's all very elementary. It's a bit like a puzzle. So you first show that. Well, for every element in A, there's a unique element that you can compose it, a unique element in E that you can compose it with, and that then defines the source map. And then you check little by little associativity and so on. Or I should say, of course, the one important thing is the graph of the groupoid multiplication, of course, is the graph of this, Dirac morphism, right? But you have to check that this graph defines a groupoid multiplication. Right, so it has this groupoid structure. E is a subgroupoid. And if you have a Dirac action, then it's the total space of this P, of the Courant algebroid P, has a groupoid action. So for groupoid action, you always need the so-called moment map to the units. And so all this comes automatically. So this then eventually boils down to our original definition of Dirac Lie groups from my paper with David. And I should say that there are other definitions of Dirac Lie groups which are actually different. Okay, so in the main example, if you have a Poisson action on a Poisson manifold, what is this groupoid structure? Right, so in this case, the double tangent bundle of H has a groupoid structure because, well, TH, the tangent bundle, has a group structure. That's the tangent bundle of a group is a group. And T star H has a groupoid structure as a symplectic groupoid. And you just take the direct product of the two. Well, and TH acts on TM, and T star H acts on T star M. So the action of T star H on T star M is a grouped action where the moment map in this case is just the usual moment map from symplectic geometry. So the grouped structure, of course, in practice is a very convenient way of actually describing the multiplication morphism if you want to do some generalizations. So even in the theory of Poisson Lie groups, this grouped structure is used a lot because one checks that so that the simple characterization of having a Poisson Lie group structure is that the graph of the bivector field has to be a subgroupoid for this groupoid structure. So that's how you usually check it. And you have a Poisson action if L is a submodule. Okay, so here's an example of a Dirac Lie group that is not a Poisson Lie group. So just take any as in Hassen invariant matrix typo. So suppose you have any Lie algebra given as the Lie algebra of a Lie group H, and suppose it comes equipped with an invariant metric. And I'm going to denote by H bar the same Lie algebra with minus the metric. So metric for me just means non-degenerate symmetric bilinear form. Doesn't have to be positive definite. Okay, then we get a Dirac Lie group where the current algebroid is H times Lie algebra H plus H bar. And the Dirac structure is H times the diagonal H. And the way in which this becomes a current algebroid is using an action with coisotropic stabilizers. And the action is just such that the first H acts by left multiplication, the second H acts by right multiplication. So what this notation here means is tau L are the left invariant vector fields, tau prime R are right invariant vector fields. Right, so one factor acts by left multiplication, the other one acts by right multiplication. And this has coisotropic stabilizers, even Lagrangian stabilizers. Right, so it defines a current algebroid, and we immediately have a Dirac structure. And in this case, for this to be Dirac Lie group, I also need the multiplication map, which I describe as a groupoid multiplication. And here's an obvious groupoid structure on H times Lie algebra H plus H bar, where you just take the Lie group structure on H and the pair groupoid structure on Lie algebra H plus H bar. And so this is a Dirac Lie group. And that's the Dirac Lie group which is responsible, so to speak, for the theory of Lie group value mode maps. And you can cook up many examples of Dirac actions of this Dirac Lie group. So for example, Lie algebra H plus H bar has a natural action on the Grassmannian of coisotropic Lie subalgebras. So we take coisotropic Lie subalgebras of any dimension, and we ignore the fact that that's singular. So maybe take some smooth manifold contained in the Grassmannian of coisotropic Lie subalgebras. And so you have an action of H plus H bar on that, coming from the left and right action again. And this action has coisotropic stabilizers, because at any given coisotropic Lie subalgebra, the stabilizer contains that coisotropic Lie subalgebra. And this leads to lots of examples of Dirac actions. For example, again, you can take the Grassmannian of Lagrangian Lie subalgebras. Consider the case that H is a semi-simple Lie algebra with the metric the killing form. Then there's a nice description of the wonderful compactification of the group H in this framework. So the wonderful compactification of H in this case has one of these Dirac actions. So that's a very nice example. Okay, so let's get to the classification. So for the classification of Dirac Lie groups, I need this more general notion of a Dirac Manin triple. So Manin triple had a non-degenerate, was a triple of Lie algebras, and D had a non-degenerate symmetric bilinear form. So now I'm just considering any element beta in the second symmetric power of D, which is at invariant, but it doesn't have to be non-degenerate. So might as well be 0, for example. And the only thing I require about G and H is that the Lie algebra G is what we call beta coisotropic. So if you view beta as a bilinear form on D dual, then it vanishes on this annihilator of G. That's what we call beta coisotropic. So there's no assumption on H. So the only assumption is that D is the direct sum of G and H as vector spaces. So the definition is no longer symmetric between G and H. So no extra assumption about H. Okay, and the classification goes in those terms. If beta is 0, then there's no assumption. So any Lie algebra triple would do.
Or G could be D, H could be 0.
That's also possible, yeah. So there's also no assumption that G and H would have the same dimension. No, it's a very general thing, of course. And in principle, there should be lots of examples of such Dirac-Meinrenken triples. Questions, do you find interesting examples that you actually care about? Well, the one example, I should say that we used, and that's the example that plays the role for this Cartan Dirac structure, which, say it again, is important for our theory of Lie group valued mode maps, is where this triple DGH would be H plus H bar. Then G is the diagonal. And this H would be H plus 0. Right, so in this example, so this was where H has a metric. In this example, you see H diagonal is Lagrangian, so in particular it's coisotropic. But on this summand, the bilinear form is actually non-degenerate. So it's by no means Lagrangian. Okay, so the classification goes in those terms. So first of all, the Dirac Lie groups are classified by the H equivariant Dirac-Meinrenken triples. So again, there's a slightly more general notion of H equivariant, where the Lie group H acts on D by automorphisms, preserving beta, and so on and so forth. And as far as the Dirac homogeneous space is concerned, well, I'm just stating a special case of the result. So Dirac manifolds of the form H mod K, with the additional property that H mod E acts transitively on P mod L, are classified by co-isotropic, beta co-isotropic Lie subalgebras of D, which are K invariant, and such that L intersect H is equal to K. Now, so it's the exact analog of this Drinfeld classification in this case. So what I'm using here is A was a group point over G. E was also a group point over G. Then one can show that A mod E is actually a group. And likewise, P mod L becomes a space on which this group acts. So if you also assume that the group acts transitively on that space, then you have this classification. So we also have a classification without that assumption, but then it looks a little more complicated. Okay, so that's how the classification goes. And let me say a few words about arguments that we use in doing this classification. So the key point is, again, this strange action of H, which is not by coherent automorphisms. Now, suppose you have a Dirac action on a Dirac manifold. Then the group H acts on this coherent algebra which you have over the Dirac manifold by this formula. So the action on some element Y is given by the group-wide action of X, where X is the unique element in E for which it is defined. So what one uses here is that E is a group point over G, and the source and target maps for E are fiber-wise automorphisms. So this element X, for which this group-wide action is defined, is actually unique. And that's the fact one uses to define an action. So there's this action which is not by coherent automorphisms, but as before, we have the fact that invariant sections are closed under the coherent bracket. And we can use this in our examples. So, for instance, if I take my Dirac manifold to be the Dirac Lie group H itself, I immediately get that by taking the quotient under this action, I get a man impair, because I get a Dirac manifold over a point. So I get a man impair QG. So that's not yet this Dirac Meinrenken triple that I'm aiming at, but that's what we get. So we get this man impair, and we get then a trivialization of our Dirac structure. All right, but so to get this Dirac Meinrenken triple, I need one more ingredient, and the way to do this is to generalize Lu's theorem a little bit to this context of Dirac actions. So just like we had in Lu's theory that if you take in Lu's theory, the result was that if you take the cotangent Lie algebroid together with the action Lie algebroid, the direct sum has a Lie algebroid structure, which is H invariant, and is very useful. So we have the exact analog here. So if you take our Dirac structure L, together with the action Lie algebroid, the direct sum has a Lie algebroid structure, in such a way that both summands are Lie algebroids. And this Lie algebroid structure is actually H invariant. So this strange action, this bullet action which I have on L, does not preserve Lie algebroid brackets, but on this direct sum, it's by automorphisms. And the way one proves this is actually kind of nice. I mean, it shouldn't say much about proofs, but it's really quite nice. So you simply take your Dirac manifold M together with the Dirac Lie group H. So you just take the direct product, but the Dirac structure which we take on H is just the standard one, double TH, and the Dirac structure is TH, the tangent bundle. You just take a direct product like that. So on this direct product, our Dirac Lie group still acts. So we have the Dirac action on M lifted to a Dirac action on H times M. And the result of this simple trick is that now the action is free, and so I can take a quotient. Right? And that's how I get a new Dirac structure over M. And that's all. So this, in this way, if I just take, so this new Lie algebroid that I obtain is simply you take TH times L and take a quotient by H. That's all. Oh, I forgot I have to finish. Sorry, I forgot I have only 50 minutes. So I should just I can basically, when it's finished here, I just want to say that this is the trick which we now apply to this QG. QG has another Dirac action. So you lift it, you get some Q hat, G hat. And that's how our Dirac Meinrenken triple comes about. Okay, and then I'll just finish here. Yeah, I don't think so. I mean, it's certainly been much examined, in particular by David in the context of supergeometry, and I suppose that then is very very close to that. And so many of these results, I believe, have simpler proofs in terms of supergeometry. The only problem being that I don't understand those simpler proofs.